This is a lovely basic animation. Okay, so the asteroids will more or less be rotating in formation either ahead or behind. They reflect the sun onto this point, creates a tangential thrust, and goes this way. The benefit is the plume of gas or debris is designed to go this way. So it goes through the formation orbits. So if they're not affected, you reduce the contamination effect. This is the other one. Again, the AEPs are moving towards and farther away from the NEO. This is done with a very minimal control law, or a control of very, very minimal control to basically keep the spacecraft such that it follows the AEP. We also did a navigation strategy to say we need to know a few things. One, we need to track the asteroid in inertial space. Secondly, we need to know where our beams cross. And thirdly, we need to orient that point where they all cross onto the correct spot on the asteroid. So we developed a navigation strategy to do that based on an onboard camera. Say for a 5 spacecraft formation, every spacecraft has a camera that's oriented towards the NEO. If we take a picture and produce a 2D image plane, you can find the center. All right. If we assume that each spacecraft has inertial measurement, like it knows where it is in space based on ground measurements and knows its attitude, then each of the spacecraft in the formation can find, if they center on the NEO, they should be, the beam should cross. Okay. This is an idea of, if this is the asteroid you modeled with points, if you map the points onto a camera plane, you essentially end up with this. This is exaggerated, but the errors are due to pixelation from the camera. All right. The blue is the estimated center, and we used a very simple algorithm, just the mean values of the vertical and horizontal. And the red is the actual center. If we do this for every pair, so 20 pairs in this 5 spacecraft formation, then we can end up with a set of values that we can filter and determine one common position for the NEO. Looks like this. If we assume a camera with a 1768, it's easier to assume square. CCD size, pixel size of 0.5 micrometers, and a focal length of 2.5 millimeters. We also introduced measurement errors on the inertial position measurement of the spacecraft and also the attitude quaternions. The blue lines here represent the distribution of the 20, like the points from the 20 spacecraft. So it's the standard deviation of the set of 20 points in. And this blue line represents, in our case, a mean value. But in reality, a batch filter would give you a better estimate. Even here, with a very large 1 kilometer pointing error, with a relatively okay camera, we can get it within about 10 meters of the actual center. We also did mass estimates for both the direct imaging and the laser option, based on current technologies, predicted technologies, so TRLs of 2, 4, and 6, and then various margins accordingly. We sized the reflector for the adaptable mirror. Okay, we assumed nominal size of 3,000 square meters. So based on this one, which is TRL 6, it's 20,000 kilograms per spacecraft. Okay. They go down by a factor of 10. So with 0.5 kilograms per meter squared for the density of the material of the reflector, it's about 2,700 kilograms. And this one, albeit it's a TRL2, however, it gets down to about 800, 900 kilograms. All right. We also have to add in, we assumed a bus probably comparable to the NEO spacecraft. So plus 20% margin is about 500 kilograms. For the reflector laser concepts, we actually worked out 4 different mass budgets. One is based on an adaptive mirror with the laser. The benefit is that we eliminate the need for the secondary, or the tertiary directional mirror, but we add more mass because the mirror itself is more complicated and therefore has a heavier density. This is with the fixed, this is the adaptive. They're pretty similar, in fact. We also did 2 solar arrays. This is actually with the solar arrays flat into an indirectly pumped laser. This is with standard technology now. This is with predicted advanced technologies, roughly about 1,000, 1,500 kilogram difference. We were looking at these just because we were curious what the actual mass difference was between that and a more reflective mirror concept. All the masses include cooling system for solar arrays, lasers, cables, reflectors, radiators, etc. An interesting thing is when we looked at the direct imaging system, previous studies had assumed you needed a minimum concentration ratio of about 2,500 or 700. When in fact, if we do direct imaging, we don't. We found it's actually better to increase the number of spacecraft than increasing just the concentration ratio. Okay? This is the concentration ratio from about 10 to 90. This is the number of spacecraft you require. Okay? And this is the deflection distance. All right? So if we have a warning time of 4 years before, so we start the thrust 4 years before, primary mirror of 60 meters, and using the adaptive with direct mirror, say you have a concentration ratio of 50, okay? Red is a fairly large deflection. You need about 8 to 10 spacecraft. Same thing with the laser option. Because the efficiency of the laser is much lower, due to any number of techniques, the fact that it has mono frequencies, much larger losses. So if we say an operating efficiency only 20%, you need a much higher concentration ratio because you have a much lower power coming in. Again, number of spacecraft, concentration ratio, and deflection distance for only 20 meter diameter, warning time again of 4 years. In summary, both options are feasible at this stage. It will depend on the mission or in trade-offs which one you would like for a particular mission, but from a technical point of view, they're both feasible. And they both have advantages, disadvantages. They can both be placed in proximity to the asteroid. We avoid the sort of plume and debris. We avoid blockage. We avoid shadow and sun from the orbit. Navigation is feasible, assuming we can data fuse the variety of measurements. The mass of the system is directly proportional to the area of the reflector. So again, it comes up with the idea that many small spacecraft are better or more technologically feasible than one large one. And again, the lower concentration factor is more effective than sort of many satellites with lower concentration factor is better than a few mirrors with a very large one. And last but not least, the other benefit is because a lot of these technologies are independent of the development of this mission. So the development into solar array technology is independent from us. It'll increase on its own based on other market demands. Same with lasers, either directly pumped or indirectly pumped. The deployment of large, lightweight, flexible structures into space, for instance, for Ashiki, and as well adaptive shape control of flexible structures in space or on the ground. And that's it. Thank you.